Welcome, everybody. My name is Keith Randall. I work at Google on Go, and I work primarily on runtime and compiler issues. And today, I'm going to be talking to you about maps. So I hope everyone in this room has used a map before. There's a lot of detail with maps. I can't cover everything today, so there's going to be a lot of stuff I'm sweeping under the rug that I can't talk about. So if you have any questions, if things look weird, you're not sure what's going on, it's probably because I swept it under the rug. And feel free to come find me later and ask me about it. With that said, the first thing we have to cover is what is a map? So a map is just a mapping from keys to values. So in Go, to make a map, you just have to pick what your key type is going to be and what your value type is going to be. And then there's a bunch of operations you can do on the map once you make one. You can insert a new mapping from a key to a value. You can ask, hey, I have this key. What's the corresponding value for that key? And then you can do other operations like delete. You can iterate through the whole map and find all the entries in the map. And you can ask for how many entries are there in this map. So this is sort of this typical stuff you'd get out of reading the spec in the Go language spec, which was talked about in the last talk. The one thing you do need to worry about is that the key type needs to have an equality operation. So most types in Go have equality operations. All the integers, all the floats, structs, interfaces all have equality defined in them. A couple types which don't are maps, slices, and funcs. So you can't use those as keys in maps because there's no equality operation. You can't ask the question, hey, is this key equal to this key in order to get anything out of the map. So those are disallowed. Any value type is allowed for the value for the map. The type that's being returned can be anything. One of the keys to maps is that they're supposed to be fast, that if you look something up in a map or you insert something into a map, it should be constant time, so that no matter how big the map is, the operation should take the same amount of time. And that is, for the most part, true for Go maps. So what would you use a Go map for? We have these awesome maps. We want to do something, and we want to profit. We want to make a lot of money with maps. So how do we do that? And for most things, it's not really clear how to make money. But for maps, I think I have a good idea. We're going to do some stock trading with maps. So we're going to make lots of money in finance. So here is a high-frequency trading bot that I wrote. It's a dozen lines of code, and it's going to make us lots of money. So the way we're going to do this is we're going to get a feed from NASDAQ of every trade on the NASDAQ stock exchange as a channel. And this channel is going to have the symbol of the stock and the current stock price. And then we're going to have a map, and what this map is going to do is it's going to keep track of the last price we saw for every stock. And so we get a new trade from the NASDAQ stream. We look up what the last price is for that symbol. And if the current price is bigger than the last price, that means the price of that stock is going up, and we're going to buy. So we issue a buy order if that's the case. If the current price is less than the previous price, then we issue a sell order. And then finally, we keep track of what the last price we saw is by updating the map. And the hope is, I've talked to my finance friends, and they all agree that this is going to make us lots and lots and lots and lots of money. So this is going to be awesome. This is how we're going to profit from Go maps. So we'd like to use maps to make this high-frequency trading bot, but suppose that Go didn't have maps yet, and our job was to implement maps to make our trading bot a success. How would we do that? So here's a very simple implementation of maps. And this map is just going to be a slice of entries, each one being the stock symbol and the price of that stock. And so a map is just a slice, and so when we want to find a stock in this map, we just have to iterate through the slice. We compare the stock symbol that we're looking for against all the stock symbols. Yeah, we can just switch. We're switching mics. I'm not really sure why, but hopefully this sounds better for you. Yeah, so we have to look through this whole slice looking for the stock symbol that we want to find the price for. And so we basically iterate through the whole array of slices. If the key happens to match, then we return the value. Otherwise, we keep iterating until we find it or we run off the end of the slice. So this will work. The problem is it's going to be slow if there's lots of entries in the map. So the bigger the map gets, the longer it's going to take to find a stock we're looking for on average. So this is a speed fail. If we're going to have a high-frequency trading bot, it's got to be able to trade at high frequency. This is going to take too long. All the other high-frequency bots that are out there are going to beat ours to the punch. So what do we do about this? So somehow the fundamental problem here is that we have to look through all the data to find the key we're looking for. But you probably saw when registering for this conference a way to make things faster. And the way you do that is you have to split the data up. So when you registered, everyone was split up by last name as to where you registered, so the people looking for your registration don't have to look through all the registrations. They only have to look through some subset. And so that's the idea here. We're going to try to look through only a subset of the data to find the stock symbol we're looking for. So let's just split the data up. Let's pick a method. We'll do the same method we did for registrations. We just split things up by first letter of the stock symbol. So every stock symbol goes into the correct bucket for its first letter. And then when we're looking for a stock symbol, we just have to figure out which bucket to look in, which we use a very simple function of the first letter of our stock symbol. And we go look in just that bucket for the stock symbol we want to find. And so if we have enough buckets, somehow proportional to the number of items in our map, hopefully things will get evenly distributed amongst the buckets. And so each bucket will only have a couple symbols in it. And then iterating through the items in one bucket will be fast, and this will fix our speed problem. So this is sort of the fundamental idea of what we want to do. The trouble is our splitting function is not very good. So this might work for the NASDAQ, where the first letters are reasonably distributed. But suppose someone invented a new stock exchange where the symbols were not little character codes, but were URLs. This is the URL DAC. So we take all our symbols and we put them all in buckets, and lo and behold, they all fall in one bucket because they all start with H, right? Not so good. So sort of splitting things up by first letter is really not a great idea because it works for some things but not for others. And so the question is, can we find a way to split things up into buckets that always works? That no matter what kind of key you have, whether it's strings or integers or whatever else, how do we split the data up into buckets that will always work? And this is the idea of hash functions. Not cryptographic hash functions, but hash functions used for this purpose. The idea is that you give it a key, and it tells you what bucket to go look in. And a hash function needs certain properties. Whoa, that's not good. Shut up, iCloud. So the main property of the hash function is that it has to be deterministic, that if I give it a key and it tells me to go put some stock symbol in bucket 3, when I come back later and ask for the same stock symbol, it has to say bucket 3 again. It can't say bucket 2, because then I go look and it won't be there, even though it should be. So that's the main property of hash functions. It has to be deterministic. In addition, for performance, we want a bunch of other things. We want to make sure that keys are assigned to buckets essentially randomly, that keys are evenly distributed throughout the buckets, no matter what the distribution of the keys is. Also, we like the hash function to be fast. If the hash function's slow, it's kind of useless, because it's got to be at least faster than just looking through all the data. An additional property that would be nice is that it should be adversary safe. Even if a bad guy gets to pick what all the keys are, they don't all map to the same bucket. So this is particularly important for things like if you're going to put the headers for HTTP requests in a map. Those are generated by some guy on the web who's sending you requests. If he's able to pick what all those keys are so they all map to the same bucket, they're going to make your web server very slow. So you want to make sure that adversaries can't do that. The good news for this talk is that such functions do exist, and we have one in Go. The bad news is they're hard to get right. It's very easy to write a hash function that takes certain elements and all maps into the same bucket. It takes quite a bit of engineering to get this hash design right. And so in Go, we're going to do this for you. Go takes care of computing hash functions for any type you want to use for your maps. And the consequence of that is you can't define your own hash function, and as a consequence, your own equality function for maps. We take all of that and do it for you. So I'm not going to talk any more about hash functions. It's a whole talk by itself. Maybe I'll come back next year and give a talk about hash functions. But we're just going to assume for now that we have a hash function. So once we have a hash function, we know what bucket we want to go look in.
And so this is what a bucket looks like in Go. So a bucket is going to be just a chunk of memory. It's going to have 8 slots for data. So we'll have up to 8 stock symbol price pairs that can fit in this bucket. If there are more entries, randomly, you could get more entries in a bucket than can fit in those 8 slots. We have an overflow pointer, which will point to additional buckets if necessary. And hopefully that won't happen too often. In addition, at the top of this bucket, we keep a couple extra bits for each entry that keeps track of some additional hash bits for each of those entries. And that's used to do faster comparisons to check whether any particular entry in the bucket matches. And I'll go into more how that gets used in a little bit. So this is what a bucket looks like in Go. It's not particularly complicated. And this is what a whole map looks like. So when you declare a map in your function, that's actually just a pointer to a map header. And the header contains sort of all the meta information you need for your map. It contains how many entries are currently in the map, that's the length. It contains the number of buckets that we're currently using. And because it's always a power of 2, we keep the logarithm of the number of buckets to make that field smaller. It contains a pointer to where the actual buckets are stored in memory. They're all stored in one contiguous chunk in memory. And then there's some other ancillary information like hash seeds and other things, which I won't describe in this talk. The bucket pointer points to this array of buckets. You'll see here that bucket 2 has an overflow bucket because it just has so happened that more than 8 keys map to that bucket. But in general, most buckets will not have overflow pointers. At least that's the hope. So that's the layout of maps in memory. That's what a map looks like under the hood. Then we have to talk about how the compiler generates code to go look through this map. And so the obvious thing to do would be every time we see a lookup call like this, we compile it to a runtime call. We say, hey, runtime, I'm looking for this key in this map. Please return me the value. Now the question is, what is the type of this lookup function? And after you think about it for a little bit, well, it's the type of whatever K and V and M are. We just sort of plug those in, but they're different at different call sites in your program. So what we actually need is some sort of lookup call that's parameterized by type. So the type of lookup depends on what the key type and the value type is of the map, which means we need generics to implement map. So this is a generics fail because Go doesn't have generics. And this isn't a problem just for maps. This is a problem for slices. This is a problem for channels. Sort of any generic type that's predefined in the language, we'd like to implement it in Go, but there's no generics in Go. So how do we implement generic data structures in Go without generics? It seems like sort of a catch-22. Even like append. How do you do append without generics? Well, we're going to fake it. And so this is sort of the general technique we use in the runtime to implement all these generic operations. What we do is instead of having the values that we're passing around like keys, you can't have a key in the runtime because you don't know how big it is, you don't know, how to copy it, all that kind of stuff. So instead, the runtime is going to work exclusively with pointers to all the generic data structures we care about. So instead of having a key, we'll have a pointer to a key, and instead of having a value, we'll have a pointer to a value. And we'll use unsafe pointers, which are pointers to anything inside the runtime. And then, now that we have all the keys and values as unsafe pointers, we also need to know things like, well, how do I hash this thing? And so we'll have, in addition to all the keys and values we're passing around, we'll also have type information that we have to pass around for all these things. And the type information will be stored in type descriptors. So the type descriptors provide all the operations you need on the items. Like, they give you the size. That means you know how to copy them from one place to another. They give you an equal function. And the equal function, we pass a pointer to 2 different keys, and it tells us whether they're equal or not. And that's it's key type dependent. Similarly for the hash function, we pass a pointer to the key, to the hash function, and some seed stuff, and it gives us back a hash value. And then, of course, for maps, there are 2 parameterized types, the key and the value type. And so for map types, we have this little wrapper that we use to pass both of them into the runtime at once. All right, so that's how we're going to fake generics. So now let's look at what lookup looks like now. So lookup compiles to something a little more complicated now. So instead of just passing the key into the runtime, we first take the address of the key, we cast it to an unsafe pointer, and then we pass that pointer into the runtime. Similarly, we pass the map, we just sort of cast to a map header pointer, which is easy. And we have to pass also the additional type information to runtime.lookup. And then when it returns, it doesn't return a value, it returns a pointer to the value, at which point at the call site, we can cast it back to the concrete type we care about and dereference it to get back the value that we want. And now, the type of the runtime function lookup actually has a type that I understand. It takes a pointer to some struct, that's the type information. It takes a pointer to a map header, which is also some struct. And it takes an unsafe pointer, which points to the key. And it returns an unsafe pointer, which points to the result. So that we can actually implement. And so here is the actual implementation out of the runtime, cleaned up a little bit for display, but otherwise, this is exactly what the code is in the runtime. So the first thing lookup does is it checks to see whether the map is nil or it has no entries. If that's true, we just return 0. We know there's nothing in the map. Otherwise, the next thing we need to do is figure out what bucket to go look in. And to do that, the first thing we need is to hash the key. So to hash the key, we need to know what the hash algorithm is for that key, and that's stored in the type information. So we take the type. I have my little thingy here. Right here, we take the hash function out of the type information. We pass it a pointer to the key, some seed information from the map, and that gives us back a hash value. Then we use that hash value to figure out what bucket we're supposed to go in. We take the low bits of the hash value to decide what bucket to go in, and then we also store the top 8 bits of the hash value. We store those in an extra field, and I'll show you what we do with that in a second. And then we compute where the bucket is in memory. And so that's also kind of complicated because the buckets are different sizes depending on what the type of the keys and values are. So if your key's very big, your bucket's going to be big. If your keys are small, your buckets are going to be small. And so we actually have to do pointer arithmetic to figure out where the bucket is. Of course, Go also doesn't have pointer arithmetic. So in addition to no generics, we have no pointer arithmetic. So we have to sort of fake it with unsafe pointer. And that's what this add function does. It sort of casts unsafe pointers to uint pointers, adds them, and then casts them back again. So that's how we figure out where the bucket is. So once we have a bucket, we just have to iterate through it and look for the key we're looking for. So here, we just iterate through the 8 entries in our bucket. The first thing we do is we check these extra bits. And so what this basically is doing is a very fast check for whether the key actually matches or not. And so if the top 8 bits of the key we're looking for, the hash of the key that we're looking for, does not match the top 8 bits of the entry that we're looking at, then we know those 2 keys are not equal, and we can just skip the rest of this computation. So that's like a 3-instruction thing to check those top 8 bits. So that's very fast. So we can go quickly through the bucket to find the one entry that might actually match. And then we have to compute, where is the key in this entry in the bucket? That's another unsafe pointer arithmetic calculation. And then we have to call the equal function for the key type. We give it a pointer to the key we're looking for and a pointer to the key that's in the entry in the bucket. And if that returns true, that we found the key we're looking for. And we just return, again, this crazy computation that tells us where the value is in that bucket, the corresponding one to that key. And if we go through all 8 entries, we don't find what we're looking for, then we have to look through overflow buckets. And so that last little bit just looks through overflow buckets, if there are any, until we find what we're looking for. If we don't find, so this is basically all there is in the lookup implementation. There's a bunch of additional stuff for things like the race detector and other stuff that I've sort of swept under the rug that's in here. If you actually go look at the real code, there's more stuff. But this is all the code that runs in the normal case. The implementation of insert and delete looks very similar. You just do something different when you find the match. The one thing that's different about insert is that we have to sometimes make the map bigger during insert. So when we're doing an insert and we decide that, hey, these buckets are too full, I'm getting too many overflow buckets, I need to make my bucket array bigger. And so this is what's called growing the map. We have to make it bigger. And we do this when the buckets, they're size 8, when on average the buckets have 6.5 entries in them. we decide to grow, and that's sort of empirically determined. So the way we do it is we allocate a new array of buckets. It'll be twice as big as the old array of buckets, so hopefully we'll only have half as many entries per bucket. We copy over all those entries from the old buckets into the new buckets, and then once we're done that copy, we can throw away the old buckets, and then we use the new buckets that are now twice as big. And then we keep doing that, and if you keep inserting, eventually that'll happen again, and you'll grow it again, twice as big. The process of copying can be expensive, and if you do it all at once, you're going to induce a large pause to whoever called it. Like you do lots of inserts, and they're all very quick, and then all of a sudden you hit the insert that grows the map, and that insert would be very slow. So instead of having that happen, we're going to do this copy incrementally. So every time we do an insert or a delete into the map, we'll copy a few entries over from the old buckets to the new buckets. And after several inserts and deletes, eventually we'll have copied everything over, and then we can drop the old buckets. In the meantime, we have a bunch of buckets. We have both old and new buckets, and all the operations on the map will be a little bit slower because we have to look in both places to see if we can find the key we're looking for. But that's how we grow. So let me just change gears a little bit and talk about how Go maps compare to maps in other languages. So I've selected 4 other languages more or less at random, ones I know, and compared what Go maps do versus what other languages can do. The first thing you might think about is, can I take the address of a value slot, someplace in the bucket in my map? And in Go, you can't do that. And in all of the other languages, except for C++, you can't do that. And the reason is because it interferes with this growing procedure. So if I take the address of some entry in a bucket, and then I keep that entry around for a long time, and in the meantime, the map grows, then all of a sudden that pointer points at an old bucket and not a new bucket. And that pointer is now invalid. So it's hard to provide the ability to take the address of a value in a map without constraining how grow works. And I believe that's what C++ does, is it does grow in a different way so that you can take the address of a bucket. And in fact, if we go back here, you'll notice that we actually do take the address of a value in the bucket. That's what's returned by runtime.lookup, is the address of some slot in a bucket somewhere. But we ensure that the compiler ensures that that pointer does not live past that last line there. So we take the address, we return it, we use it, and then we drop it before any grow can happen. So that pointer has a very limited lifetime. Are you allowed to modify a map during iteration? Most other languages don't allow you to modify maps during iteration. Go does. And this imposes a bunch of constraints about how data in maps are laid out. That the reason why we use overflow pointers and not some other hashing technique where we do open addressing of some sort is because of iterators and being able to modify maps during iteration. Can you provide your own equality and hash functions for maps? In all of the languages, you can do that. In Go, we don't allow it. It's very easy to shoot yourself in the foot by defining maybe an equals and a hash function that aren't compatible, or a hash function that's not good for certain input data. So in Go, we don't allow that. Are maps adversary safe? That means if someone who's a bad guy is selecting the set of keys that go into your map, does the map still perform well? And in Go, yes, we have an adversary safe hash function. In most other languages, the hash functions proper are not adversary safe, although Python has fixed theirs recently. In Java, they switch data structures if they notice the buckets are getting too big. They switch to a binary tree. So like each bucket is now a binary tree. It's kind of crazy. In C++, you're sort of out of luck. You have to write your own adversary safe hash function if you want that. And then let's just look at a little bit about how fast and how much memory maps use in these different languages. Python's pretty bad, although that may be as much the badness of Python's timing measurements as the actual map. You notice that most of the other languages are pretty good. Java's particularly good. They have very low lookup time. So you'll see in the vertical axis here, this is nanoseconds per lookup versus the size of the map that you're looking in. And even at 100,000 elements, map lookup times are only in the sort of 25 nanosecond range for Java, and maybe in the 35 range for C++ and Go. So they're pretty fast. I wouldn't read too much into the exact comparisons amongst the compiled languages here, just because it varies so much by processor type and the type of the keys and values you're looking up and so on. But they're all pretty fast. This is how much space your map uses. Again, Python's kind of weird because it's very hard to measure how much space you're actually using in Python. And you'll notice that there's a line down at the bottom here, and that's the minimum possible memory you could use for this map. And this is basically the memory that my very first implementation would use. If you just had to keep all your keys and values in a slice, this is for maps from N64 to N64. So it's just to keep the entries themselves would take 16 bytes. So you'll see here that most of these other implementations use about a factor of 2 more space than the minimum possible. And you'll see here that Java uses more than Go, for example. Go is designed, the buckets are big so that we can pack data in very well, and there's only 1 overflow pointer for every 8 entries. Java sort of has a different trade-off where their buckets are smaller, but that means that they use more space because there's more overflow pointers and so on. But they're all trade-offs. So to conclude, we're pretty much out of time. Use maps. They're a versatile data structure for the 21st century. The space overhead is not too bad. It's about 2x what you would use otherwise. The speed is 100 cycles to get something into or out of a map. So it's not a memory read or write, but it's a divide or maybe 2 divides worth of cost. Okay, that's it. Thank you.